So last time we were able to, I think, finalize on both the morphinans and the benzomorphans. And of course, we are starting with the morphine ring, or with the morphine molecule rather, and we are removing some of the extra baggage, and we are still realizing that the molecule, even first of all, of course, on the loss of ring E, it had activity. Now we lost ring B, it still had activity, but we did mention when it loses ring B, there are some remnants which are left, two substituents, and they must carry a certain orientation. The orientation of those groups which were left, where previously ring B was, their orientation we realized was very important. You could have the alpha, you could have the beta, and depending on the orientation, of course, as we mentioned last time, there will be differences in potency, and once you have differences in potency, you will also have differences in toxicity, because we say the higher the analgesic activity, the higher the potency. So we are moving on, and all we need to establish in every group is whether the morphine rule is maintained. So in all the groups you are looking at, kindly check whether the morphine rule is maintained. All we are doing is removing some of the rings, and indeed still realizing that even on removal of some of the rings, we still have activity. The activity could decrease. The activity, the potency could decrease or increase depending on the substitution, as we already said. So to this morning, we should be able to look at the 4-phenyl piperidines and hopefully also the propyl amines. So I think that is the last slide, as I have been advised. We want to start on the 4-phenyl piperidine. And when we look at the 4-phenyl piperidine, now we are down to only 2 rings. When we look at the phenyl piperidines, that's why we call them phenyl piperidines, we have only 2 rings. We have the phenyl ring, which is to cause the aromatic ring, as found in the morphine, and we have the piperidine ring, again as found in the morphine. We have knocked out. We have removed the ring E, which was the first one to remove. We have removed ring B, and we removed ring C. So now we are only at 2 rings. And if you look at this structure, indeed, if you look at this structure, can you tell me, or look at it, let us look at it together, is the morphine rule still in place? And indeed it is, because some of the requirements of the morphine rule is the tertiary nitrogen. We still have the tertiary nitrogen. Another requirement is that the quaternary carbon, let me put the pointer before I am advised. I've remembered, thank you. So if you look at this is our tertiary nitrogen. So our tertiary nitrogen is here. That's our tertiary nitrogen, and that is a requirement for activity. Another requirement was the quaternary carbon, which was our carbon number 13 in morphine. You can see we do have that. Another requirement was that the quaternary carbon and the tertiary nitrogen are separated with 2 carbon atoms. That's 1, and that is 2. I was hoping that I put the bigger one. So this is 1 carbon there, and that is the second carbon there. So that again is there. And of course, a phenyl ring was also another requirement. So if we look at basically the morphine rule, this molecule is indeed obeying the morphine rule. So we still expect it to be able to bind the narcotic, or bind the narcotic receptor, either the K or the mu, as we had already discussed. We look at again this molecule, the numbering. We are starting again, just like we did with the benzomorphans. We are starting with the nitrogen, but this time we are naming the 2 rings differently. So we start with the nitrogen, that's position number 1, 2, 3, 4, 5, 6. And then the benzene ring, we name it as a prime, 1 prime, 2 prime, 3 prime, 4 prime, and so on. When you look at this compound, again, you will see it can have substituents at various points. Again, just like morphine, the terminal nitrogen can be substituted with either small groups or bulky groups. You see what is the inference. And then, of course, here, our quaternary nitrogen here, sorry, our quaternary carbon, the quaternary carbon, which is position number 13, remember it was alias had earlier substituents coming from this, but now we can also still have our substituent coming from that quaternary carbon, which is now our position number 4. We can have a substituent there, and we look at that substituent, we realize that that substituent can change. It can be a ketone, can be an ester, it can be a reverse ester with retention of activity. Then still at position number 4 is where we are getting our benzene ring. And the benzene ring, you can see it is directly attached to that position. As we move on, we'll also realize that you can separate the benzene ring with a nitrogen, just one atom, from the quaternary carbon, and to get what we will call the anhydride piperidines with due retention of activity. Kindly note also, on position 3' of the benzene ring, you do have a substituent, which is usually a hydroxyl group. And when you put a hydroxyl group at that position, you generate a new set of compounds we call the bemidones. But they are still phenyl piperidine, but in their own category of bemidones when you put the hydroxyl group at that position. We'll also learn that this piperidine ring can also be substituted at position number 3. You can substitute that piperidine ring at position number 3 and still have another set of molecules with a slight, with another one different change, with another structural modification, get still compounds that have good analgesic activity. Stereochemistry, of course, is too important, and we'll note that as we move along. So that is the general structure of the phenyl piperidines, or that's the structure of the phenyl piperidines. And we can say this is now the general structure of the phenyl piperidines, where we are saying that is our terminal nitrogen there, which we are giving R1, can be substituted with various groups. You see, like we look at piperidine, where it's a methyl group. We look at anilidine, where it is an ethyl piperidine group. So it can be it has an amino group and it has an ethyl group. So you will see that you can have different groups again at that position. R4 is the position I was telling you that the piperidine ring can be substituted with a methyl group. That's position 1, 2, 3. Remember, we are counting from the terminal nitrogen 1, 2, 3. So position 3 of the piperidine ring can be substituted usually with a methyl group. Again, we realize that that methyl group here can either take the alpha or beta orientation. And depending on the orientation it takes, it will influence the structure of the phenylpiperidine and therefore the way to bind on the receptor. Then we have our R3 and R2. One of them is usually the phenyl ring, but it can change. And that's why we are putting it as R3 more often than not a phenyl ring. But you see, the phenyl ring can be substituted. It can also change as like in the anhydride piperidines, and that's why we have given it an R3. And then the R2 is what we have said. It can be an ester, it can be a ketone, it can be a reverse ester with differences in the activity. And with that now, we can look at some of the compounds, and I hope you can be able to draw these compounds out, to draw them out so that you can be able to see the differences. So we are saying that meperidine is our prototype in the 4 phenyl piperidines. Meperidine or pethidine. This is also the drug we call pethidine, a very popular drug, especially in labor ward for analgesic activity. It has lesser potency than morphine and therefore lesser toxicity. And you can see our methyl group there, that one, R1, that's a methyl group. And then R2, as we have said here, a phenyl group. And then R3 is this one. And you can see this is an ester, C double bond O, C2H5. And therefore, sometimes these compounds are called ethyl derivatives. So this is indeed an ester. R3 is an ester where you have a C double bond O, C is O double bond O, O C2H5, and that is meperidine. And for meperidine, this R4 is a hydrogen. Then we have bemidone, and I have said the difference between for the compounds that we call the midones or the midones. The midones is whereby the phenyl ring has a meta-hydroxyl substituent. So if you look at the difference between meperidine and bemidone, the only difference is that bemidone, the phenyl ring has a hydroxyl group. So that's the only difference. And then you have properidone. Now, if you look at properidone, again, you have a methyl group there, a phenyl group there. It is actually the group that is there. It is the group that is there as you here you had an ethyl ester, but if you look at this, it is only the group which is different, where you have COC, CH, COC, CH. So this is a branched. There is branching here. So in properidone, it is just the branching which is making a difference. The group that is there is branched, and that is the only difference. And then you have the ketobemidone. So here again, ketobemidone, a slight difference. Of course, being a bemidone, being a midone, you must have a hydroxyl group as you had there, and then it's a keto. It's a ketone. So in place of the ester that is found in piperidine, you have a ketone, C double bond O, C2H5. So that's the only difference. Then we go to another name, alpha protein. Now this name is actually giving us a structure. And if you look at alpha protein, you see it has two differences from meperidine. The methyl group is still N-methyl group there. You still have a benzene ring, but here there is a mistake. Kindly correct this. Sometimes they make a mistake in their structures. This is not the correct structure. This should be what we call a reverse ester. The alpha protein will have a reverse ester, whereby the structure should be C first, should be the reverse, whereby when this group by joins, it joins fast. This is C double bond O, so this will join with O first. So this should start with an O, then C double bond O, then now it joins the C2H5. And so on. So that's continuous. So all I'm saying here, this is what we are calling here, it is a reverse ester. By meaning it's a reverse ester, instead of starting with the C double bond O, the ester is reversed, and the structure starts with an O. O is the one which is directly attached to carbon number 4, not the carbonyl group. I hope that is clear. And then, of course, as a difference again, at position R4, you have a methyl group. So here, in all the other compounds, you had a hydrogen, but the proteins, the compounds we are calling the proteins, are compounds that have a methyl group at position number 3 of the piperidine ring, and in addition, their ester is reversed. So when you see the name protein, it means that phenylpiperidine has a methyl group at position number 3 of the piperidine ring, and in addition to that, the ester that is found in meperidine has been reversed. So you have a reversed ester. So that is our alpha protein. So you can have beta protein and alpha protein depending on the orientation of that group. It can either be a beta orientation or alpha orientation. Again, the beta one will have a lot of toxicity. It has a much higher toxicity, much higher analgesic activity, and therefore much higher toxicity, and therefore not clinically preferred. So you prefer the alpha derivative because it has lower analgesic activity and therefore lower toxicity. Then we go to the next compound, which is anilaridine. And when you look at anilaridine now, you see all the others have an N-methyl group. Is where I was saying this group now in anilaridine. In anilaridine, this group changes, and you can see now it is a CH2 anethyl phenylamine. It's an ethyl phenylamine. So it's a bigger group joined here. So remember this group, you are taking it the whole of, you can see this is a CH2. So take this CH2 and you come and join it here. So it will be here CH2 phenyl ring, and an amino group. So that is the difference there. This position, we still have the benzene ring. Here we still have the normal ester, just like in meperidine, and the hydrogen. So the only difference is the substituent at position number one of the piperidine ring. Then from there, we get another group of compounds. And these other group of compounds are the ones we are calling the anylidopipelidines. And the first one is fentanyl. And I believe you have heard of fentanyl. And when you look at fentanyl, fentanyl is a compound that is used as a general anesthetic. It's a general anesthetic, and you can see it's R1 again changes. R1 changes. Remember this group, we are putting it here. So the R1 becomes CH2 phenyl ring, very close to anilanidine, anilaridine, very close to anilaridine, but of course without the amino group. So that group, large group, is attached there, and then you find that it doesn't. So it has that that group there, and then it has a hydrogen there. And now, so one of these groups here is a hydrogen, one of those groups, a hydrogen, because you find that it's phenyl ring. It has a phenyl ring, but its phenyl ring, which is here, is such that this you have, sorry, so you have here on this group, you have a nitrogen. So at this position, you have a nitrogen, and then when you have your nitrogen, it is attached. It's a nitrogen here, which is attached to the phenyl ring, and also attached to the ketone. So that there is still, the compound still has a phenyl ring. It is the arrangement that is different. That at our position number 4 here, you do not have the two substituents. You have one substituent. One of the substituents is a hydrogen. The other substituent is also carries the phenyl ring, and of course it carries a nitrogen, and then the nitrogen is the one which is substituted with a phenyl ring, and of course the other substituent. In other words, in these compounds we are calling them anylidopiperidenes, we do have that the piperidine ring is separated from the benzene ring with a nitrogen. That is the only difference, and you see how that helps in the activity of these compounds. And all the others are the same, or the only thing is that the R1 will differ. The only thing is that the R1 will differ. You can see for fentanyl, which is a prototype, the R1 is a hydrogen, but for the others, you find that R1 is not a hydrogen. It has been substituted with other groups with retention and indeed increase in activity. You can see fentanyl still has the same group, but now R1 is an ester, and the same group there, and CH3. So I think you can look at these compounds. All we are saying is that they do have different substituents at the different positions, and of course, once you have the different substituents at the different positions, there will be change. That is what we call structure activity relationship. The different substituents will be responsible for differences in the pharmacological activity, and therefore one molecule might have more activity than the other. But it's important for us to look at this molecule, diphenoxylate and loperamide. What are those compounds used for? Diphenoxylate and loperamide. What are they used for? Can you remind me? Diphenoxylate and loperamide. What are these compounds used for? good answer. That's correct. They are used as anti-diarrheal agents. In other words, one of the side effects of narcotic analgesics is to cause constipation. It's usually a major problem even for these drug abusers. But the structures of these compounds have been so altered such that they have very high lipid solubility. They are retained within the periphery. They bind the GIT receptors. They bind the GIT receptors to act as anti-diarrheal agents, but because like loperamide has very, very high lipid solubility, it's not absorbed, and therefore it actually just acts locally. So you can see how structural modification of drugs or of a compound can actually even change the pharmacological use. So because we have said like the alfentanyl, sulfentanyl, or fentanyl, and fentanyl are actually anesthetic drugs. And I believe you mentioned them when we were looking at the general anesthetics. But now diphenoxylate and loperamide have a very huge structure, and they are huge structure. You can see the group that is found here, and they have different substitutions, and that structure allows them to be used completely differently because it alters the ability to penetrate the BBB, but allows them to bind the receptors within the GIT. And once they bind the receptors within the GIT, they are able to bring about, or they are able to be used as anti-diarrheal agents or to bring about constipation in patients who are having diarrhea. So you have now, I just decided to draw this so that we can understand when I was talking about the alpha protein. When I was looking at the compound, I mentioned the alpha protein and the beta protein. We are going to look at it. I wanted us just to understand about this methyl group here. At position number 3, of this piperidine ring. This is a piperidine ring. At position number 3, you can have a methyl group which can either look down or be vertical or horizontal. It can be vertical or horizontal. It is horizontal in the beta protein. It is vertical or axial. It's axial in the alpha protein. Depending on its position, it will have it will alter the distance between the phenyl ring and the terminal nitrogen. And once it alters the distance between the phenyl ring and the terminal nitrogen, it will alter the way the molecule will interact with the morphine receptor. It will alter the way that molecule will interact with the morphine receptor. Having alpha protein where this is axial, where this is actually axial, it's axial, where this is facing down and this is facing up. So that this, remember, faces up and this is facing down. Although this is also called axial, but this is facing, we consider that it's facing down and this one is facing up. So we call them alpha. And that alpha has much less activity than when in the beta, the methyl group is facing the horizontal, while this is facing up. And it's found that the beta binds the receptor much better than the alpha, but definitely the beta will also have more toxicity than the alpha. I just drew out, as I said, it's important sometimes to draw out the structure so that you can be able to see them. So again, this is anilaridine. And all we are saying is that nitrogen there is which was bound to CH2, phenyl NH2, and you can see a phenyl ring, and you can see that is an ester group there. And I just was drawing them out, or just do those out so that we can be able to understand the way the structure is. Structure activity relationship, and the representative for phenylpiperidine, meperidine, was actually the prototype. In addition to antispasmodic activity, it was found to have analgesic activity. Also found to have analgesic activity. It follows the morphine rule, and you can always do that. As we had already said, it has a terminal nitrogen, which of course is basic. It has a tertiary carbon, it has a phenyl ring, it has a quaternary carbon, and so on. All those we had looked at. It does obey the morphine rule. When you look at the meperidine, and that is a structure, it is a prototype. It has lower potency. It was found to have lower potency than morphine. It was found not to interact with the receptors as well The receptor, remember you talked about receptor, the receptor D, the receptor C, receptor B, and receptor A. So it was found not to interact so well with the receptor D, with the receptor B, and receptor C as morphine. But it was found to interact. Remember the receptor we called receptor A. It was found to interact with receptor A, which was an additional receptor. And the drugs that bind receptor A do not have as good activity as those which bind DC and B receptors. But it was found to bind that receptor, have good analgesic activity, have lower potency, but because of its structure, it has, you can see, it does not have, it doesn't have any free hydroxyl group, and it has much higher lipid water partition coefficient, and therefore will move very well across the membranes, and therefore bring about very high activity. However, it has a very short duration of action because of the fact that it is an ester. Remember, esters will be metabolized in the GIT and therefore fast pass effect. So it will have load, it has a short duration of action, being an ester, very readily metabolized in the GIT, to have moderate bioavailability, again because of that ester hydrolysis. It will on oral administration, of course, due to the fast pass effect. It has higher oral it has higher parenteral potency than oral. This was a mistake. It has higher parenteral potency than oral because, of course, when you give it parenterally, it will avoid the fast pass effect. It will, in the GIT, you will attain very high concentrations within the brain because, of course, we have already said it has very high lipid water partition coefficient. And unlike the other morphine analogs, we have looked at have about 3 to 4 rings. They are rigid. When you look at this, you find that there is the single bond. There is this single bond. This phenyl ring is attached to here with a sigma bond. It's attached through a sigma bond. And because it's attached through a sigma bond, it means it can undergo rotation. It can rotate. And once it rotates, it can either be axial or horizontal. It was found that when it is axial, it has maximum binding on the receptor D, C, and B than when it is horizontal. But unfortunately also, the axial conformer has higher energy than the horizontal conformer. So you will find the concentrations of the axial conformer, which is best or which optimally binds the receptor, are much lower than the concentrations of the horizontal conformer, which does not bind the receptor well. And that is why it is thought to have lower potency than morphine, because the conformer that binds the receptor well, which is supposed to be the axial conformer, is in low concentration because of its high energy level. And this is brought about by the fact that it is not rigid. This molecule is not rigid. It is flexible. It can rotate. It has these sigma bonds, and therefore this ring can rotate. And like when you look at the morphine, 5 rings attached to each other, very rigid structure, and therefore the structure cannot rotate. So it has rotation around the sigma bond, and the benzene axial, you can see arrangement, gives the highest activity because of its ability to bind the receptor. The axial conformer is at a higher energy level than the horizontal conformer, which exists in higher concentrations. So I hope you can follow that. Therefore, the meperidine may bind the receptor in a slightly different way from the rigid opioids. It has a low receptor affinity and low antitussive activity. It has a low receptor affinity because what you require to bind the receptor, as I have said, is the axial conformer, which is also in low concentrations because of the fact that the axial conformer has higher energy level. Molecules will always want to exist in the lower energy conformer. It has a low receptor affinity that binds with the A and the anionic site D because, of course, it has that anionic site. It's not able to bind very well with the B and C sites on the morphine receptor. Binding with site A is not as effective as binding with site D. So that's why we are saying it will have lower potency. You can't be able to explain its lower potency. It has lower potency than morphine, because it is mainly binding with site A, and it is rather than binding with site rather than binding with site D, which gives maximum activity. And its binding ability, as we have said, has been reduced by the fact that the axial conformer, which should bind the receptor well, is in very low concentration because of the issue of energy levels. We've already mentioned some most of these things we have mentioned. We're looking at the general SARs. We are seeing the esters and reverse esters at the position 4 are active. So you can have either the ester or the reverse ester. I think we can go to that and finish with that mara moja. So when we talk about the ester and the reverse ester, this is exactly what we are talking about. So you remember for meperidine, this was a C double bond O, and then this was an O. When we look at the proteins, when you look at the proteins, this is indeed what we are calling the reverse ester here. It is a reverse ester because it is not like the normal ester which was found in meperidine. The ester which was found in meperidine when the molecule was synthesized was C double bond O. So when you have a reverse ester, as I explained before. So when you have a reverse ester, and then you have a substitution at position 1, 2, 3. That is when, of course, you get the proteins. Now, once you have the reverse ester, there are some you bring about some stability as well as some instability in vitro. When you have the reverse ester, you find that the reverse esters are more stable. So we can just follow here. Another molecular modification that stabilizes the molecule is reversal of the ester. The meperidine reverse ester, which we are calling N-methyl phenyl for propionoxyl piperidine. For propionoxyl, remember this is position 4. We are calling it propionoxyl because this is 1, 2, 3. So this will be a propionyl. Remember, whenever you have an acyl group, you call it propionyl. Propionyl to end up with N-nyl. N propionyl. Y L propionyl. So remember when we do nomenclature, these two last letters are replaced by the other group. So this is an oxo group. So you replace this YL because we are looking at this as a substituent, and you leave the N and then you put oxy. So propionoxy. Propionoxy is representing the propionyl group and the oxygen. So don't ask yourself, what is this name? So the whole of this group, propionyl, oxy. So but since when you do nomenclature, you remove the YL, just like we do methyl. Methyl is from methane. You remove the NE and you put YL. That's the same thing we are doing. So it becomes 4-propionoxyl piperidine. So N-methyl, and then at position number 4, you have propionoxy, and then, of course, the piperidine is the name of that compound. So we are saying that compound has a longer duration of action due to increased resistance to ester hydrolysis. So the reverse ester is more stable to ester hydrolysis. But unfortunately, the ester group converts a stable group into a living group in the vitro, not in vivo, that produces MPTP. When you talk about MPTP, it should be the same N-methyl phenyl, but now this becomes tetrahydropyridine. So this here, that compound there, when you put the reverse ester, is readily in vitro, it's readily converted to this compound, and it's the one we are calling MPTP. And I've said MPTP will be the same. We are saying it's N-methyl phenyl, and then this is one, this carbon, if it was pyridine, you'd have a double bond. You'd be having a double bond. You'd be having a double bond there, there, and there. So remember, if you have piperidine is that compound. Piperidine is that compound. That compound, make it like that. Pyridine is that compound. It has a nitrogen for sure, and then it will have double bond, and double bond. So that's piperidine. So once you remove that bond and you remove that bond, you have added 4 hydrogens. So we are calling, that's why we are calling this N-methyl phenyl tetrahydropyridine. Tetrahydropyridine. So that it will form that, and this compound is very readily metabolized by monoamine oxidase B. Remember, you have monoamine oxidase A, monoamine oxidase B, and once it is metabolized, it will give us now the pyridinium. So this is now the pyridinium, and this molecule is even said to be carcinogenic. So upon composition, which is then converted now to again the same N-methyl phenyl 4, this time pyridinium. So that is why it is P, pyridinium, and it will be protonated. Pyridinium, that's a compound by the monoamine oxidases. So you can't see, we are always trying to look at the chemistry, that you have changed that molecule, and once you change that molecule, you get what we are calling the proteins. You get the proteins once you change once you change that molecule, you get the reverse ester first. You get the reverse ester. The reverse ester is more stable because of the structure. It's more stable to ester hydrolysis, but it can easily be converted to MPP plus. The plus means because of the protonation, and once that happens, then we are saying that is in vitro. But in case it does happen in vivo, that compound has been said to be actually carcinogenic. That is important. Then now after that, we are saying introduction of a methyl to this compound here, which of course now let us give its short name MPPP. Once you introduce a methyl group at position number 3, results in stereoisomers having different potencies. You can have the transmethyl, which is called the alpha, and also you can have the cis isomer, which is a beta protein. And of course, the beta protein is more active than the beta protein is more active than the alpha protein. So now I go back, and this is where we are. So we have trans is alpha protein. So you can see this one looking down, that is facing down, or having the alpha orientation, whereas that has the beta orientation, that's looking up, having the beta orientation. This is twice as active as morphine formulation, and that is the trans isomer. And the beta isomer is when this is having the beta orientation, the other one is having the beta orientation. That gives us beta proteins. So they are only proteins when they have that alpha methyl group. And all we are saying is that this orientation, depending on that orientation will make a change on the final shape of this molecule. And the final shape, depending on the shape you have, there will be one shape or one conformer which will fit the receptor optimally and therefore give you maximum activity. So, of course, the higher the activity, the higher the toxicity. I just wanted to finalize on that. And you can also see also when you look at this is a structure of meperidine, but note for all of them, the active conformer of the meperidine, which is best fits the receptor, is when the phenyl ring takes the axial orientation. When the phenyl ring takes the axial orientation is when these molecules best fit the receptor, as we have already said. You are here. I just wanted to go so that we finish off with the reverse esters, and I hope you have understood the reverse ester, the consequences of the reverse ester, also that you can do substitution at position number 3 to get beta proteins and alpha proteins. The simple ketones are active, and indeed we did give an example of that. Ketones are also active. Gave an example of ketobemidone, and the ketobemidone has a ketone at that position, so you can give an example of the ketobemidone also having activity. Propyl is the optimal chain length, again just going back to our structure. Or we are saying normally the propyl, whereby you have 1, 2, 3, ignoring that oxygen. If you look at the explanation, it says ignoring that, the propyl 1, 2, 3 gives maximum activity, ignoring the oxygen. Propyl is the optimal chain length, excluding the ester oxygen. So in most of these compounds, you will find that that substituent at that position has a propyl group or 3 carbon atoms, because you're ignoring the ester oxygen. The phenyl ring at the 4th position of the parent ring is necessary for activity and must be able to assume the axial position. I've just shown you that. Addition of a meta-hydroxyl group will enhance activity, and such analogs are bemidones. Again, we have looked at that, and we do have bemidones, bemidone, where all that which we have here is that hydroxyl group. We have the ketobemidone, again, that phenyl ring. It is important for activity, but it can't be substituted with a meta-hydroxyl group, and that also increases activity. When a reverse ester is combined with a 3-methyl group, the analogs are known as proteins. We have already looked at that. And the methyl group may cause enantiomeric recognition by the opioid receptor. We are only saying the methyl group can bring about stereochemistry, or can be responsible of stereochemistry, or can be responsible of different shapes, and those different shapes will have different binding with the receptor, where we said, of course, we have the alpha and the beta proteins. Next, removal or replacement of the phenyl. See, again, we did mention the phenyl ring is necessary. If you remove it or replace it with alkyl, aryl, or R-alkyl groups, it always will decrease the affinity for cytase. So you require the phenyl group is needed for optimal activity. If you do, for this particular compounds, if you do a separation, you increase the separation between the phenyl ring and the phenyl ring with the quaternary carbon, again, you will also decrease activity. So if you change or if you change the distance between this and the terminal nitrogen, again, you will change activity, because again of the change in the shape of that molecule and its ability to bind the receptor. We have said insertion of a meta-hydroxyl group that we have already mentioned, the bemidone and the ketobemidone. Conversion of the ester to a ketone increases potency and duration of action by increasing metabolic stability. Ketones are more stable to hydrolysis than the esters, and of course, can be metabolic stability. Esters can be hydrolyzed, but ketones cannot. So the conversion from ester to ketone is just structural improvement, because improvement on stability by change of structure, because esters are more susceptible, as we have said, to ester hydrolysis than the ketones. This we have already looked at. I'm adding those points just in case that I don't leave any point behind. This we've already looked at. So I think we have looked at most of those positions and what is important in those positions. So let us look at the nitrogen substituent. The nitrogen substituent is a methyl in most cases, and we have seen that, of course, in most cases, because in anilaridine keeps giving me, I have a problem with my denture. When you have a problem with the denture, anilaridine, when you have a problem with the denture, it can really embarrass you. So of course, we are saying that this group here is usually a methyl group, but you can see it can change. It has been different in anilaridine. It is different in also fentanyl with retention of activity. So that is, again, whenever we say something, we like giving examples. So that is just what we are saying. that indeed it is usually methyl group, as in meperidine, ketobemidone, and so on, but it can be changed with retention of activity. A phenethyl or its equivalent will increase activity. Remember, we did mention, even when we were looking at the morphine and ethyl morphine, and we said when you increase that substituent beyond 5, then there is increase in activity because the compound is able to also join bind. In addition to binding each other receptors, it is able to bind the A receptor. So again, the same situation here, no difference. A phenethyl or its equivalent will increase activity. It is not possible to confer antagonist activity with the nitrogen substituent such as allele as in morphine. So in this particular group, you do not have any antagonistic activity by putting aryl groups or whatever. But an increase in the group, like we have seen in even fentanyl, fentanyl has also an ethyl benzene ring or a phenethyl group without the amine. The aniline has also an ethyl phenylamine group. That's the only difference. So we are saying once you increase that group, again, you do increase activity, but we cannot do substitution really to get like and the allele. Remember when we did back in the naloxons and so on, trexons, whereby we put an allele group and we were able to get nalofin, we were able to get antagonistic activity. I want to believe that we have mentioned then everything here is similar with the morphines. But the other only point we have not said is this one, that your expansion or contraction of the ring to a 7 or 5-membered ring gives compounds with analgesic activity, but less mu receptor affinity due to change in the relationship between the nitrogen and the phenyl ring. So you can increase the size, you can decrease the size, but it's of no benefit. The resultant compounds will have much, much lower activity. And again, this is because we did mention there is a relationship between the benzene, the terminal nitrogen, and the phenyl ring, because these are groups. Remember, the phenyl ring binds a receptor through hydrophobic interactions. The terminal nitrogen binds a receptor through ionic bonding. So, of course, this position, the sites within the receptor are fixed. The sites within the receptor are fixed. So somehow the distance between these two groups also requires to be within a certain distance. It must be within a certain distance so that it can be able to interact with these receptor sites which are fixed, because the receptor sites for morphine within the host will not change, they are fixed. So the molecule also must, like, remember, even when we were looking at even antihistamines, we were saying we require 5 to 6 angstrom. You require a specific distance between the phenyl ring and the terminal nitrogen, so that when that drug approaches the morphine receptor, it will interact with the D, it will interact with the B, it will interact with the C. If it has other substituents that can allow it to interact with the A, it will also interact with the A. So that's why you're saying if you change the molecule, you change the shape, you will either improve on the interaction or you will decrease the interaction. Then we look at now the molecule that we were talking about. You can see this is the structure of the diphenoxylate. Again, you can see that is our position number, position 4, where you have a phenyl ring, and you can see you have an ester at that position. So when you look at diphenoxylate, you can see it borrows a lot from meperidine. There is a phenyl ring, and of course also there is there our ester. But at position number 1 is where you have a very huge substituent. You can see at position number 1, there is a very huge substituent. At position number 4, at position number 1, you can see you have a very huge substituent. This huge substituent increases the lipid water solubility, the lipophilicity of this molecule. Of course, there is balancing. You can see here a very small polar group to balance the water solubility, so that at least the drug can go into solution for purposes of absorption. But for sure, when you look at this molecule having similar structural features as meperidine, but also differences at the position number 1, having a very huge group, and therefore it is not, it does not pass the membranes. There is deputization, remains within the periphery, and therefore brings about its activity within the periphery with no CNS activity. So diphenhexylate is high lipophilic, and you can see why. However, in regular doses, it has no CNS activity due to a highly protein bound and sequestered in the lipid bilayer. So because of this high lipid water solubility, it has highly protein binding. It has also high sequestering. When you talk about sequestering, it is what you call deputization. It will be retained within the periphery, within the lipid layers, because of its high lipid solubility. It also is rapidly hydrolyzed to the carboxylic acid, diphenoxin, which cannot penetrate the blood-brain barrier. This group here, I doubt it's hydrolysis. It is this group here which will be converted to the carboxyl. Because when you say hydrolysis, it's kind of hydrolysis, but I would rather say that group there is oxidized to the carboxylic group. When you say hydrolysis, you will go to this, and I believe, but I'll look at that structure. Let me just confirm that structure. I didn't, but I want to believe the nitrile group. I want to believe. Let me just confirm whether it's the one, whether it's a nitrile group. Yeah, it's correct. It's this one which is hydrolyzed. Diphenoxin. Good always to confirm because I was not very sure. Yes, it's actually a hydrolysis. So we are saying it has a very short duration of action. It's rapidly hydrolyzed. That is this group again. It's still an ester. So this ester is hydrolyzed, and once it's hydrolyzed, it will give us the carboxylic group, and that's what we're calling the diphenoxin. And that diphenoxin again with a free carboxylic group. Carboxylic groups have high polarity, highly ionized in the blood, again cannot penetrate the BBB. But as we had said earlier, the first reason why it will remain in the periphery is because of its high lipid solubility, sequestering or deputization, all of course being bound to the plasma proteins. And the little that you have is able to bind the peripheral analgesic or narcotic analgesic receptors, giving us antidiarrheal activity. Again, loperamide, also very high. Again, if you look at the structure of loperamide, you have, of course, that benzene ring, and you can see that benzene ring has also, is even further having an added group, a halogen. Halogens increase lipid solubility of aromatic compounds, increase lipid solubility of aromatic compounds. They will also decrease because the electron withdraws through resonance, through not resonance, but through negative inductive effect. The electrons withdraws through negative inductive effect because halogens have higher electropositivity, electronegativity. In other words, they pull electrons more than carbon. So they will pull electrons from the benzene ring through negative. So they will pull the electrons through negative inductive effect. They pull the electrons through negative inductive effect. And once they pull electrons through negative inductive effect, they will decrease the reactivity of a benzene ring, and therefore its rate of oxidative hydroxylation will go down. Its rate of oxidative hydroxylation, because of the pull of electrons from the ring through a negative inductive effect, will go down. And once the metabolism goes down, it means, one, the halogen has increased lipid solubility because it has high lipid solubility. Two, it has also decreased the rate of metabolism of loperamide, further giving it a longer duration of activity. So that's what we are saying therefore. And again, if you look at that molecule, again, you see at the nitrogen, you can see again the two phenyl rings, a very small portion here, which is adding. Remember, you always must take care of water solubility, because if you completely diminish water solubility, then the molecule will not have activity. It will not go into solution, and therefore will not give us any activity. So therefore, you find that there is very high lipid solubility. Molecule has very high lipid solubility, and because of that very high lipid solubility, again, it gives us activity within the periphery. It has high lipid water partition coefficient, also free of OCNS effect due to high protein binding and twice as potent as diphenoxylate. Further, the high lipophilicity results in slow dissolution, resulting in slow absorption and 40% bioavailability. So, of course, when you have very high lipid water solubility, most of it, the drug will not go into solution. Remember, the drug must go in solution for absorption, and then it gets into the receptors within the GIT. But the little that gets in has very high binding to the receptors, giving us the antidiarrheal activity. The lack of water solubility prevents drug abuse because it cannot be injected. So that drug is not cannot be formulated into parenteral formulations because of poor water solubility. So what we are saying, you can't see what structural modification of a compound can do. We started with morphine, went to the morphinans, went to the benzomorphans, now we are now at 4-phenyl piperidines. And under the 4-phenyl piperidines, we are seeing you can also have some structural modification. You get the bemidones, you get the prodines, and then we are seeing finally you also get compounds that have shared structure, have structural similarity with the 4-phenyl piperidines, but have absolutely a different pharmacological application. They have a different therapeutic indication. They are used as antidiarrheals and not as analgesics. We do have one example of an phenylpiperidine type of an antagonist, but you can see, of course, it has a very, again, complete different structure. Again, it is a bemidone. You can see it what we had earlier. It shares that. It also shares on the methyl group that is on the piperidine ring. Again, here you'd have removal of all the other groups that we have there as ketones or esters. You have a methyl group there and a completely different structure here, whereby you have a highly soluble group at that position. And this was found to have antagonist or mu antagonist activity. It was found to have mu antagonist activity, and that compound is called alvimorphan. Alvimorphan was found to have mu antagonist activity, and as we had said earlier, you can see this group here has no close resemblance with the allyl groups that we were putting, in the morphine or in the benzomorphans to give us antagonistic activity.